Okay, so the recording is started and we shared the screen. Okay, so I think that last lesson we drew the level curves of this function, and then we have to study this the second part of the exercise. So we have the following utility function for the consumer, so xy over 4x plus 3y. Then we have to assume that X commodity costs 6 per unit and the Y commodity costs 9 per unit. And we have to find out how many units of each commodity should the consumer buy in order to maximize utility. Okay, so we have fxy which is, I think, 4x plus 3y, and maybe xy at the numerator, yes, okay. Okay, so x 6 per unit and y 9 per unit. And we have to find how many units of each commodity should the consumer buy. Okay, so we have that x costs 6 per unit and y costs 9 per unit. Okay, so if I have an amount of money, which is k, I need to have a quantity that I cannot go upside, because if I have infinity money, I can buy infinity x, infinity y, and then I can maximize my utility. So I suppose that my amount of money is k, and in this case, if I buy x quantity of X commodity and the Y quantity of Y commodity, of the second commodity, I spend 6x plus 9y. And this quantity has to be equal to k, because this is my amount of money. Okay, so, but I think that we saw in the last lesson that the constraint has to be 6x plus 9y equal to k. Okay, so we have to maximize this quantity with the constraints 6x plus 9y equal to k. And this is a problem that can be solved with the Lagrange multipliers. So I tell you in last lesson that the first step is to prove that there exists a maximum. And this is done in the last lesson. So we proved that the constraint is closed and bounded. And then the second step is to use Lagrange multipliers. So we have to, if this function is called fxy, but this is actually called fxy, if this function is called gxy, then we have to solve this system. The derivative with respect to x minus lambda, the derivative with respect to x of g, equal to 0. Then the derivative with respect to y, the same equation, but we derivate with respect to y. And then the constraint. So this. We need to solve this system. Solve and find x, y, and lambda. Okay.
Sorry, Professor, this is the first step. Yes, right?
Now, this is the second step. The first step we did in last lesson. So we have to prove that there exists a maximum. So in last lesson, we proved that...
we find the critical points and we prove that there is a maximum.
There is a maximum because this function is continuous and the constraint is closed and unbounded. So we use the Weierstrass.
Okay. But in the test, will we have to do that, or is it always like that?
Well, I think that I can ask Professor Porretta, but I think that you have to do. In general, the method is almost always the same. So you have to prove that your constraint is closed. It is always closed because if there is a equal here, is closed, and then that this is bound, that it is bounded. Bounded, it means that x cannot have to lead, x and y has to lead in a bounded domain. So x has to be smaller than a constant and bigger than another constant, and the same for y. But I think that you have to prove.
Okay, thanks.
Okay, then we have to solve this system. So I think that I can... I just want to write here the constraint. Okay. Now, in order to solve it, we have to compute the derivative with respect to x and with respect to y. So the derivative of f with respect to x, well, this is f, this is a ratio, so we have the denominator square, then we have the derivative of the numerator with respect to x. So in this case, y is a constant, so it is like 2x. The derivative of 2x is 2. The derivative of yx is y. Then times the denominator minus the numerator times the derivative of the denominator. So the derivative of 4x with respect to x is 4. And the derivative of 3y with respect to x is 0 because there is no x here. So this quantity is constant with respect to x. So the derivative of this is just 4. Okay. And in the same way, we compute the derivative with respect to y. Okay. So the derivative of this quantity with respect to y is x, because this quantity x in this case represents the coefficient, y is the variable. And so the derivative of a first order polynomial is just the coefficient. So x times the denominator minus, well, the numerator times the derivative of the denominator. As before, in this case, this is a constant with respect to y, so the derivative is 0, and the derivative of this is 3. Okay, we can do, if we want, a little computation here. So the derivative, so we can compute the product. So 4xy plus 3y squared minus 4xy over the denominator square. So we can simplify here and we obtain just this. And then here we have 4x squared plus 3xy minus 3xy over 4x plus 3y squared. So we can simplify also here and we obtain 4x squared over 4x plus 3y squared. Okay, and then the derivative of g with respect to x. Well, this is very simple, it's just 6. And the derivative of g with respect to y, also this is very simple, and this is 9. Okay, now we have all the quantities we need. The derivative, this other derivative, the derivative with respect to y, the constraint. So we have all. And we can solve this system. So I want to write this system. Well, maybe I can write here. Then I erase all the stuff and I will copy here and we start to solve. Okay, so 3y squared over 4x plus 3y squared minus lambda, well, gx is 6, minus 6 lambda is equal to 0. Then 4x squared over 4x plus 3y squared minus the derivative of g with respect to y is 9, so minus 9 lambda is equal to 0. And finally the constraint, which is 6x plus 9y is equal to k. Okay. Okay, perfect. Now I want to copy this part of the exercise, but maybe with the copy I can do just an initial computation because I want to compute lambda from here. So lambda I can.
Professor,
Yes.
sorry to interrupt, but when we have to evaluate the factor lambda, we can give for granted that is always different from 0.
Lambda? No, lambda can be also 0.
Okay.
Okay. So I just want to put lambda here and then divide by 6 and obtain this. Here the same, I put lambda in the right hand side and then I divide by 9 in order to compute lambda. And last, the constraint. Okay. Okay. Why I do that? Because now I know that lambda is equal to this quantity, but lambda is also equal to this quantity. So in order to solve this system, I can compare these two quantities. And I obtain that this quantity is equal to this quantity because they are both equal to lambda. Then the constraint and one of these equation, for example, the first. Okay. This system actually is very easy, this part of this equation, because we can simplify here. The two denominators are equal. So I can remove by multiplying by the same quantity. We note that, of course, there is an existence condition here. Of course, for x plus 3y needs to be different from 0. But okay, this existence condition, I think, appears also in the level curves of the function. So here, so in our exercise, we already have this condition. So when we compute the value of x and y, we need to require that for x plus 3y needs to be different from 0. Okay. Well, here I can also simplify 3 and 6. Okay, also here, of course. So I have y squared over 2 equal to 4x squared over 9. Then 6x plus 9y equal to k. And then lambda, which is equal to y squared over 2 4x plus 3y squared. Okay. Okay, from the first equation, I can compute y squared equal to 8x squared over 9. Then I can compute the root, and I obtain y equal to the square root of 8 is just 2 square root of 2, because 8 is 4 times 2, so the square root of 4 is 2, and then I have the square root of 2, x over 9. I don't want to put plus or minus because, of course, Of course, x and y needs to be positive.
I'm sorry, isn't it over 3?
Over 3, yes. So x and y needs to be positive in case equal to 0, but it cannot be negative because they represents the units of commodity bought. So they need to be a positive quantity. So I can compute the square root here without problem, just putting y and x here. Okay, I can use this in this equation. So we obtain 6x plus 9 times 2 square root of 2 over 3x is equal to k. And then lambda, which is equal to y squared over 2 multiplied by 4x plus 3y squared. Okay. Now I can solve the second equation. So this equation depends only on x. And so I can solve and I can find x. So we simplify here. We obtain 3 times 2 is 6. So I want to factor 6. 6x I can factor and I obtain 1 plus square root of 2. From here 1 and from here square root of 2 equal to k. So this means that I can divide by 6 times 1 plus square root of 2 here and here. Okay. And we obtain the value of x. Okay. Then the value of y, which is just 2 square root of 2 over 3 times this quantity. So I can simplify here. And we obtain the value of y, which is just square root of 2k over 9, 1 plus square root of 2. Okay. Well, I can compute lambda if we want, but this is not important. I'm just interested, I'm only interested in the value of xy.
So Professor, sorry,
Yes.
when we are computing Lagrange method, we we do all the stuff for computing x and y, not lambda. Then when we find x and y, we can leave lambda.
Yes.
It doesn't deserve any more for us for the calculus. I mean.
Yes, it is irrelevant for the final result, but you need to check that you can find lambda. So if, for example, I find a solution x equal to 0 and y equal to 0, then if I put here, I obtain 0 at the denominator, so I cannot find lambda in this case. So this solution is not good because
okay, we can use it like a proof for our calculus to find if we are computing well.
You need to be sure that you can compute lambda, that there exists lambda solution, but you don't need to compute directly.
And just the last question, lambda could be also be negative or not?
Yes, of course.
Okay.
Okay, so we have our solution. So our solution is our maximum, if you want, is k over 6 times 1 plus square root of 2 and square root of 2k over 9, 1 plus square root of 2. And this is your maximum point. Okay. Okay, so I interrupt for one moment my screen. Do you have any question, any request for a kind of exercise, some typology of
Yes.
exercise?
I have an exercise.
Yes.
I don't know if the classes agree on that. Is on compounding, like the first part.
Okay, you can send in the chat the.
Professor, after this exercise, may I ask you some questions about other types of
Yes,
exercise?
of course.
Okay.
I sent in the chat. It's the first one. Thank you.
Okay, so I see also other question. Well, marginal analysis, I think the exercise, maybe then we can do this exercise about marginal analysis. And then, okay, so about the Hessians, yes, we obviously we need to do other exercise about the calculus of maximum and minimum in with the computing of the Hessian matrix, but of course with the Lagrange multipliers. So we start with this exercise.
What about the like when the Hessian is equal to 0? What are we supposed to do?
Well, it is a little bit difficult. I don't know if in your exam you will have the Hessian equal to 0, because in this case the classical computation failed, and you need to look at the function and try to understand by hand, if you want, trying to understand if this point is maximum or minimum. It is a little bit difficult. Maybe if we have time, I can send you an exercise, of course, with this example, or if we have time, we can do some exercise about that, but I'm not sure that this can appear in the exam. Okay. So first exercise. I think if it is with compound interest.
Yes, it's the first one.
Okay. Okay, so I share my screen. Okay, a certain bank offers an annual interest rate of 3.4% compounded monthly, while another bank offers an annual interest of 3.5% compounded quarterly. A competing bank compounds its interest continuously. What is the least nominal interest rate should the competing bank offer in order to be more convenient? Okay. So, we have our formula. So the capital of time t, the final capital, is the initial capital 1 plus r over n to the nt, and in the continuous case This is E to RT. Okay, so in the first case, 3.5% compounded monthly. So the first case is, well, the initial capital, of course, is the same. 1 plus, well, 3.4, so 0.034 over 12, because it is compounded monthly, raised to 12t. Okay, then the second one, one plus, the second one is 3.5% compounded quarterly, so 0.035 over, it is compounded quarterly, so over 4, because each 3 months, 40. And the third one is this, so compounded continuously. Okay, so first we need to know which is more convenient between the first and the second. So our question, first question. The final capital in the first case is greater than the final capital in the second case. Well, we write the equation. 1 plus 0.034 over 12 raised to 12t is greater than this. Well, we can simplify C0. We can do some computation here. I think we need a calculator. Well, maybe Wolfram Alpha can be very useful in this case. Okay, so we need to compute this quantity. So this is 1 plus 0.034 over 12 raised to 12. We forget about the t. Okay, 1.035. Okay, so the first one is 1.035 to the t. And the second one, we have to compute 5 over 4 raised to 4. Also 1.035, but here it was, so we need another number here. So this was 345, and this is 354. Okay, so the answer is no. This is not greater than that, so CF2 is more convenient. The second choice is more convenient than the first one. So this is more convenient. Okay. Now, the second question is we need to know how the real interest rate needs to be in order to make this choice the most convenient. Okay. So, in order to be this choice the most convenient, we must have that this choice needs to be more convenient than this. Of course, if this is more convenient than this, it will be more convenient than that because this is smaller than this. So we must have that CF3 has to be greater than CF2. The final capital in the third case needs to be bigger than the final capital in the second case. So in this case, the final capital is C0 E2RT, and in that case is C0, we just did the computation, 1.0354 raised to T. Okay, we simplify C0, we obtain E2RT bigger than 1.0354. So RT needs to be greater than the logarithm of this quantity to the T. So RT needs to be greater than, I can put this T value here. Okay. Then I can simplify, can divide by T. So R needs to be bigger than the logarithm of 1.0354. We have Wolfram alpha here. So compute logarithm of 1.0354. Okay, this is 0.0347, so 348 approximating. And this is, okay, 3.48%. So R needs to be greater or equal than 3.48%. And this is the solution. Okay, so I think that most people want the marginal analysis. So our next exercise will be marginal analysis. And then, yes, of course, some exercise about local maximum, minimum, and saddle point. Okay, a Cauchy problem. And also at least another exercise about Lagrange multipliers, because Lagrange multipliers almost always appears. Okay, since there is no time to do another exercise before the pause, we do a 50 minutes break. We can start in 15:10. Okay.
Thank you very much.
Okay, guys, we can start again. Okay, so in the chat that the problem actually wasn't finished, but the end of the problem is quite easy.
Yeah, don't worry.
Okay,
Thank
we
you.
can do if you want.
No, I talk with some of my classmates and
Okay.
thank you anyway.
Okay, so now this exercise about marginal analysis. The first part is about marginal analysis. The second part actually is about Lagrange multipliers, so it is perfect. The weekly output of a certain plant is given by this quantity, where X is the number of skilled workers and Y the number of unskilled workers employed at the plant. Assume that 30 skilled workers and 28 unskilled workers are currently employed. On account of marginal analysis, would you advise to increase the number of skilled or unskilled workers? Is the question. Well, we start writing. Okay, so I think I can quit. Okay, so fxy xy is equal to 3x plus y plus 3x squared y minus 6y squared. Okay, we know that the first part, x is equal to 30 and y is equal to 28. Okay, so the question is if it is more convenient to increase x or to increase y. Okay, in general, the growth of a function, I just want to do an example in one dimension. The growth of a function is represented by the derivative. And we know that if the derivative is positive, the function increases, and if it is negative, the function decreases, of course. But if the derivative is bigger, the function increases more rapidly. If it is smaller, it increases more slowly or less rapidly if you want. In this case, the increase with respect to x, so if we increase the number of skilled workers, the growth of the function is represented by the derivative of f with respect to x. So if we increase x, the growth of the function is represented by f of x. Of course, if we increase y, it is represented by f of y. So the two partial derivatives represents the growth of the function if we increase just one variable. Okay, in our case, we want to do what is more convenient. So if the derivative with respect to x, of course, in our point, so in 3028, is bigger than the derivative with respect to y in 3028, so increase x is more convenient.
So, sorry, we have to see which is the biggest one.
Yes, we compute the two derivatives, fx and xy and fy. We evaluate it in 3028, and then we see which number is bigger. Okay, so the derivative.
Okay, sorry, and the bigger is the most convenient.
Yes, the biggest one is the most convenient. Because if fx is bigger, this means that if we increase x, the growth will be more rapid, and so it is convenient. Okay, we derivate with respect to x, we obtain 3 here. Just 3 because the derivative of x plus y with respect to x is 1. If we derivate this with respect to x, we obtain 6xy. So y is a constant, it remains. The derivative of 3x squared is 6x, and here minus 12x. Okay, and the derivative of fy with respect to x, the derivative of f with respect to y, it's just 3 here. Here the derivative is 3x squared, and minus 6x squared, the derivative is 0 with respect to y. Okay. Now we evaluated these two derivatives in 3028. The first one is 3 plus 6 times, well, 30 times 28, this is 840, maybe. Yes. And minus 12 times x, so this one. And the derivative with respect to y, well, we have 3 times 900. Okay. So in this case, this is bigger than 4,000, of course, because 6 times 8 is 48. So this quantity is bigger than 4,800. And so we subtract this, we add this is bigger than 4,000. I don't want to do the exact computation. And this is, of course, smaller than this. We can compute exactly this quantity. Okay. I do this approximate calculus here because I don't want to know the exact value of the derivative. I want to know if this quantity is bigger or smaller than this. So this approximation is good. And this means that fx is bigger than fy. So, as said before, increase x is more convenient. Okay. So the only difficulty here is to understand what you have to do. Because when you understand that you have to compare the two partial derivatives, the computation are easy. You have a calculator, so these computations are very easy. Okay. Okay, in the second point, In the second point, we have to allocate 20 more units. So we already have 30 skilled workers and 28 unskilled workers. We have to allocate 20 more units. So how many skilled and how many unskilled workers should you employ in order to maximize the output? Okay, so you know that you have to allocate 20 more units. And these 20 units are divided by X skilled workers and Y unskilled workers. So this unit, part of this unit is represented by skilled workers and part by unskilled workers. Of course, the sum of X and Y needs to be 20. And this is the constraint. Okay, you start with 30 skilled workers. You allocate X skilled workers. At the end, you will have 30 plus X, maybe X plus 30, X plus 30 skilled workers. And you have 28 unskilled workers. You will conclude with Y plus 28 unskilled workers. Okay. So your utility function needs to be evaluated in your number of skilled workers and your number of unskilled workers. And you want to maximize this function with constraint X plus Y equal to 20. Okay. Of course, X needs to be positive and Y needs to be positive. Okay. So first step, our constraint is closed. We have to prove that this is bounded, but obviously it is bounded. Why? Because we need to prove that X is between two constants. Well, X is positive, of course, and also Y is positive. But if these two quantities are positive, you have the sum of two numbers, which has to be 20. If both numbers are positive, well, this number, X, cannot be bigger than 20. So it has to be smaller than 20. So if X is negative, if X and Y can be negative, of course, I can also have 100 plus minus 80, and this is equal to 20. But if Y has to be positive, X has to be smaller than 20, and also Y. So it is bounded. if you prove that x and y lives in a closed interval like that, so are between two constants, then your interval is bounded. So there exists maximum for f.
Sorry.
Yes.
And how do we understand in general if it's bounded or not? Like if there is x minus y, how do we understand if it's bounded?
Well, x minus y is not bounded because I can take x bigger how I want. So I can take x 1 billion if you want, and y is equal to 20 minus 1 billion. I can take 10 billions, 100 billions. So with minus, it is not constant. It is not bounded. In general, well, very often you will have this constraint.
Okay, so there isn't a general rule that we can use.
Well, the general rule, maybe the geometry can help you, because you know that you can draw this function. Well, yes, maybe this is the easiest thing. So you can draw this function, y is equal to 20 minus x. The draw is like that. You have 20 here and 20 here. Okay, in general, this is a straight line, so it goes to minus infinity and to plus infinity here. But you are in the domain where x is positive and y is positive, so you forget about this part. You look just at this part, the first quarter, when x is positive and y is positive. And in this case, the function is bounded because this is its upper limit and this is the lower limit.
Okay, thank you.
In general, you can have in your exam, you can have a function like that. Maybe you have to maximize this. So this is the constraint. If the constraint is this is an ellipsis. So you draw the ellipsis of course is bounded. It doesn't go to plus infinity. So maybe the draw can be very useful. Don't forget, never forget this information, because this is crucial. In all your exercise, x and y represents the number of money you want to use, the number of workers in this case, the number of the unit of commodity. So x and y are always positive. And if x and y are always positive, it is very easy to prove that the constraint is bounded. If you use geometry, it's immediate. So I didn't think about that, but geometry is the most rapid thing in order to prove the boundedness. Okay, so this is bounded, it is closed, the function is continuous, of course, it is a polynomial. So for Weierstrass, there exists a maximum. Okay, now we have to use Lagrange multipliers. First, we have to write the function because this is fxy, but we have to write fx plus 30, y plus 28. Okay, so this is when we have x, we have to put x plus 30. When we have y, we have to put y plus 28. So x squared becomes x plus 30 squared, y becomes y plus 28. minus 6x plus 30 square. This is equal to, well, we don't want to solve this computation. We have to compute 9,000 times 28. It is too complicated. So just this computation, x plus y plus 58 plus 3x plus 30 square, y plus 28 minus 6x plus 30 square. Okay, the constraint is x plus y, which has to be equal to 20. Okay, so we use Lagrange multiplier. So the equation is fx minus lambda gx is equal to 0. Fy minus lambda gy is equal to 0. And then x plus y is equal to 20. So the constraint. Okay, we compute the derivative with respect to x, of course, of this function. Maybe this function, we can call this function, h, in order to avoid confusion. I don't want to derivate this, but this. So maybe I call this function h. So, okay, this is f of x plus 30, y plus 28, and this is equal to h of x, y. Okay. So we have to derivate this function, not this function. Okay, the derivative of this is just 1 with the coefficient 3. The derivative of this is, well, 3y plus 28 is the coefficient, plus 28. Then we have the derivative of x plus 30 square is 2. So 3 becomes 6. X plus 30. Also here, minus 12 x plus 30. Of course, it is a composite function. So I have to multiply by the derivative of x plus 30, but this is 1. The derivative with respect to y. Okay, here the derivative is 1 times 3 is 3. Here the derivative of this quantity is 1. This is just a coefficient. Here the derivative is 0. Okay, well, the derivative of g with respect to x is 1 here. And also the derivative of g with respect to y is 1. Okay. So no need to compute 3 times 58, for example, or to compute the square, then multiply by y plus 28. You complicate the function, because when you derivate, you see you never need to compute this quantity because the derivative is 0. So it is useless. Also here, you do computation when you don't have other possibilities. So when you are forced to do computation, then you do computation. If you can avoid, it is better to avoid, because maybe there will be some simplification, maybe you don't need to compute at the end. Okay, now hx is this, so I write the system: 3 plus 6y plus 28 x plus 30 minus 12 x plus 30, then minus lambda equal to 0, because gx is equal to 1, so I can write equal to lambda. and also in the second one equal to lambda. Then, well, gx equal to 1, no, not this, sorry, the constraint. Okay, x plus y equal to 20. Okay. Okay, then lambda and lambda are equal to this quantity. So lambda is equal to this quantity and this quantity. This means, as before, we can compare these two quantities. 3 plus 6, y plus 28, x plus 30, minus 12, x plus 30 is equal to 3 plus 3, x plus 30 square. Then, for example, the second one, an equation involving lambda, and the constraint. Now, we can simplify 3 and 3 here. Now we have x plus 30 in all the terms, so we can factor x plus 30. We also can factor 3 times x plus 30. And we have 2y plus 28, so y plus 50, 2y plus 56 here, minus 12. Minus 4, sorry, because I factor 3x plus 30 is equal to 3x plus 30 square. Now I want to divide by x plus 30 in order to simplify here. Can I divide by x plus 30? Yes, because x is greater than 0. And this means that x plus 30 obviously has to be different from 0. Because this is 0 just when x is equal to minus 30, but x has to be positive, so this quantity is always different from 0. So I can divide by 3 times x plus 30. And this is very useful because I avoid a lot of computation. So now I have 2y plus 56 minus 4, so plus 52, is equal to x plus 30. And I can solve it. So x is equal to, I can find x, it is the simplest thing to find, the simplest variable to find, because there is not a coefficient here. So 2y plus 52 minus 30. So x is equal to 2y minus 22. Okay, I substitute. Sorry?
Maybe it should be plus 22.
Plus, sorry, yes. Okay, now I want to substitute this information here. So x plus y is equal to 20. This means that 2y plus 22 plus y is equal to 20. This means free y is equal to 20 minus 22, so minus 2, and y is equal to minus 2 over 3. And so x is minus 4 over 3 plus 22, which is equal to, well, 66, 62 over 3, yes. So this is the maximum point. Of course, we can find lambda here, but it is not important. This is the maximum point, but there is a problem. The problem is that y is negative. And in our hypothesis, y needs to be positive. What does this mean? This means that it is more convenient to increase x. It is so more convenient, then the best thing you can do is to decrease y and increase x more than 20. Of course, you cannot do this in practice in your exercise, because in your exercise, you need to allocate 20 more units. You cannot change the role of skilled and unskilled workers in the unit you just have. You already have. So, okay, we cannot decrease the y. So the best thing we can do, even if it is not optimal, but it is optimal in our for our restriction. The best thing we can do is y equal to 0, x equal to 20, sorry. So optimal strategy. Y equal to 0, x equal to 20.
Professor?
Yes.
2 questions. The first is about this exercise. Because before you said that once we have found to find to prove that the limit is bounded, the domain is bounded, we can find the graph through the graph of the function.
Mm-hmm.
Through the graph of the function, we can find also the maximum point.
No, because it is the graph of the constraint, not the graph of the function f. The graph of the function f is a function which is a surface in the space. It is not a line. So in order to draw it, you need to draw the free Cartesian axis, but you cannot draw a function like that. It is too difficult.
Okay.
So it is just the draw of the graph of the constraint.
And I wanted to ask you if we can do also an exercise about extinction. It was one of the exercise of the second midterm, and I found also in some of the previous exam. So if we can do one.
Okay, if you give me
Yes.
an exercise like that.
It should be the exercise 5 of the exam that I post on chat.
Okay. Okay, exercise 5. Okay, a population follows a logistic growth with the intrinsic growth rate R equal to 2 and carrying capacity K equal to 4. affected by predation from another species as described by the differential equation, okay, where k is a positive constant representing the predation rate. Find all the possible equilibrium points in terms of the value of k and discuss the stability of the equilibria. Okay. Okay, there is some typos of LaTeX, but find the value k1 such that whenever alpha is bigger than alpha 1, well, I think that alpha 1 is k1. The population will converge towards extinction as time t tends to infinity, regardless of the initial value. Okay. Okay, so we start writing. So is equal to 2y times 1 minus y over 4 minus ky over 1 plus y. Okay, so we need to find the stability points. This is the first step. So we need to discuss when this function is equal to 0. Well, I see immediately that 0 is a stability point because we can factor here y. So we obtain 2, 1 minus y over 4 minus k over 1 plus y equal to 0. So we obtain immediately 0 here. And maybe the graph is better if we just analyze the positive part. Don't need to discuss the negative one. Okay, then y is equal to 0 is a stability point, or we have to solve this equation. Okay, so we do some computation. 2 minus y over 2 minus k over 1 plus y is equal to 0. Okay, now we factor. We put in a unique fraction. So we have 4 1 plus y minus minus y times 1 plus y minus 2k equal to 0. Well, of course, we can remove the denominator because y is positive, so 1 plus y is always different from 0. We just want to know the positive value because it represents the population. Okay, so we compute here the numerator. We have 4 plus 4y minus y squared minus 2k is equal to 0. Well, this means y squared minus y squared plus 3y plus 4 minus 2k, which is 2 minus k, is equal to 0. This means y squared minus 3y minus 2, or plus 2 if you want, k minus 2. I changed all the sign. And now we have to solve this equation to find the other stability. Oh, I erase also the differential equation. Okay, now we have to solve this equation. Okay, in order to solve this equation, in order to know if there exists a solution, how many solutions, we need to discuss the sign of the delta, because the delta depends on k, so there are different cases. Okay, the delta is equal to b squared, 9, minus 4ac, so minus 8k minus 2. Okay, so the delta is 9 minus 8k plus 16, so it is 25 minus 8k. So if delta is greater than 0, and this means k is smaller than 25 over 8, two solutions, and there are y equal to 3 plus or minus, well, we know what is the delta, 25 minus 8k over 2. Okay. If delta is equal to 0, means k equal to 25 over 8, we have one solution, which is y equal to 3 over 2. And if delta is smaller than 0, then k is bigger than 25 over 8, no solutions. Okay. There is another question, actually. These two solutions are both positive. Maybe these two solutions can be, well, one of them is positive. 3 point, the square root of 25 minus 8k over 2 is positive, of course, because it is the sum of two positive quantities divided by 2. But this quantity is positive, because if it is negative, we are not interested to it. If it is negative, well, y represents the population, so the number of population. So if y is negative, we are not interested to it. So we have to discuss also this stuff. Okay, I have to erase. So maybe I want to write the information we have. We have that if k is bigger than 25 over 8, the unique solution is y equal to 0, the first one. If k is equal to 25 over 8, we have two solutions, y equal to 0 and y equal to 3 over 2. then if k is smaller than 25/8, we have y equal to 0, y equal to 3 plus square root of 25 minus 8k over 2, and we have to discuss about the other one. So we have to discuss if 3 minus square root of 25 minus 8k over 2 if this is bigger than 0. Of course, we can forget about the denominator. So we have to discuss if 3 is bigger than the square root of 25 minus 8k. We can compute the square. We obtain 9 greater than 25 minus 8k. This means 8k bigger than 16. This means k bigger than 2. Okay. So, if k is bigger than 2, this quantity is positive. If k is equal to 2, this quantity is 0, and I have the solution 0, which I already know. And if k is smaller than 2, I have a negative quantity I'm not interested to. Okay, so in order to be more precise here, if k is between 25/8 and 2, I have this free solution. And if k is smaller or equal than 2, I have these two solutions. This is the scheme of the solution. So this is just the first step. Find all the possible equilibria. Okay, and discuss the stability of the equilibria. Particular, we have to find the value k1. Well, first I think that we have to discuss the stability of the equilibria. So then when we did all the discussion, I think that these 3 points will be very easy if we do a good discussion before. So, well, the problem is that time is over. But
Professor, but how did I find 2?
Sorry, I don't understand the question.
How can we find out 2? How did we find out 2?
This, the number 2?
Yes.
Well, here we discuss about the sign of this quantity. This quantity has to be positive. If it is negative, all the negative terms are not relevant in our discussion because we want to understand what happens in the positive side. So, when this quantity is positive if we did all the discussion, and if we solve it, we find k is bigger than 2. So if k is bigger than 2 and of course smaller than 25/8, I have 3 solutions, so I can take this solution. If k is smaller or equal than 2, I have the solution y equal to 0. This solution is negative, or in case equal to 0, but I already have this information. So this quantity is negative. The negative values are not relevant in our discussion, and in the positive part, I have just to value to stability, to critical points.
Sorry, so when we have like a value as k, we always have to study it at k at delta, no, as k equal no 0 greater than 0 and not
Well, we
greater
have
than
to study just the how can I say, the 0 points of this function, just the 0 point of the function. Of course, in this study, it appears a second order equation. So a second order equation. In this second order equation, in the delta we have k, so we have to discuss the delta, and so we have to discuss k in order to find the number of stability points. Okay. So if you want, since this exercise is long, but it is very useful, because I remember this exercise also in the tutorial of last year, I think, and this is very useful because it gives the strategy, the general strategy, the more general strategy you need to use in order to study the behavior and the stability points. So I think we can stop here the lesson. I upload this lesson on YouTube, and I upload also the resolution of this exercise.
Thank you, Professor.
Okay.
Thanks very much, Professor.
You're welcome. So I also read a problem about local maxima. Well, I think that yes, it were useful if we did, but the time is 2 hours and I cannot do everything. But if you need to do some practice, you have some doubts about some arguments, you have my email address. You can write me at my email address, and we can organize, I can receive you. We can do also a linked Zoom for 1, 2, 3 pairs, 3 people who want to discuss the doubt. Okay? Okay.
Thanks very much.
Thank you,
Thank you,
Professor.
Professor.
Thank you very much,
Thank you,
Professor.
Professor.
Goodbye.
Bye.